Now there's some standard results which you can use while solving questions. And the first result is, we know that mod x is not differentiable at x equal to 0. In the same way, mod of x minus a, it is not differentiable at x equal to a. But if we have a function which is x minus a to the power n mod of x minus a, then this function fx, it will be differentiable at x equal to a if n is greater than or equal to 1, and it is not differentiable at x equal to a if n is less than 1. In the same way, we can write this function fx as either x to the power n sine 1 by x or x to the power n cos 1 by x when x is unequal to 0 and 0 at x equal to 0. Now this function fx also, it is differentiable at x equal to a if n is greater than 1, and it is not differentiable at x equal to a if n is less than or equal to 1. Now this function, if n is greater than or equal to 1, it is differentiable at x equal to a, and basically it is differentiable for x belongs to R. And here also this function will be differentiable for x belongs to R. This third point is, if fx is x minus a into gx, and this function gx, it is continuous at x equal to a, then this function fx will be continuous at x equal to a, and f dash a will be simply equal to ga. Another result is, suppose we have two functions fx and gx which are defined in the interval a to b such that fx is differentiable in this interval and gx is continuous in this interval ab, and there is a point c in this interval ab such that fc is 0, then this product fx into gx, it will be differentiable at x equal to c. Now we take an example. We have defined a function fx as x to the power 2 by 3 into sin x. Now if we look at this sin x, we know that this y equals to sin x, it is continuous and differentiable in x belongs to R, whereas this function y equals x to the power 2 by 3, it is continuous in x belongs to R, and if we find dy by dx, it will be 2 by 3 x to the power minus 1 by 3, it is differentiable in x belongs to R minus 0, and we know that sine 0 is equal to 0. So basically this function sin x, it is a differentiable function whose value is 0 at 0, and this x to the power 2 by 3 is a continuous function. So this product x to the power 2 by 3 into sin x will be differentiable at x equal to 0. And this fifth one, it is actually the intermediate value property of derivatives. The intermediate value property of derivatives, and it says, if we have a function fx which is differentiable in this closed interval ab, then in this interval f dash x will take all the values between f dash a positive and f dash b negative. Now, sixth result, it is also a theorem. It says, if a function fx, it is differentiable at x equal to a and if a is unequal to 0, then 1 upon fx is also differentiable at x equal to a. Now this basically is a corollary of fx upon gx differentiability result. And another one that we can use from here is, if we have function fx and it is differentiable at x equal to a, then f square x is also differentiable at x equal to a, because it is a composition of x square and fx, and this x square is differentiable in x belongs to R. So we can work out many more results using algebra of differentiability. Now, seventh result is, if we have a function fx which is continuous and 1, 1 defined on an interval such that this fx is differentiable at x equal to a and f dash a is unequal to 0, then inverse of this function fx is differentiable at x equals fa, and its derivative at x equal to fa will be simply 1 by f dash a. If we look at it intuitively, suppose we have a function fx which is differentiable at a and f dash a is unequal to 0 and g is inverse function of f, then we can write g of fx as x, and if we differentiate this, we can write g dash fx into f dash x will be equal to 1. Now, if we replace x with a, we can write g dash fa into f dash a as 1, or simply g dash fa, it is equal to 1 upon f dash a. That is, derivative of its inverse function at fa will be equal to 1 upon f dash a, provided f dash a is unequal to 0. And finally, eighth, we have Darbo's theorem. D-A-R-B-O-U-X, Darbo's theorem. Now, this theorem says, if we have a function fx which is differentiable in closed interval ab such that f dash a into f dash b, it is less than 0, then there exists at least one point c in the open interval ab such that f dash c is 0. And one of the corollary of this theorem is, if a function fx is differentiable in closed interval ab and f dash a is not equal to f dash b and k is a number lying between f dash a and f dash b, then there exists at least one point C in the open interval AB such that f dash C it is equal to K, which again is your intermediate value property of derivatives. Now let us take up an example. Say for example, we are given that a function from 0 to 2 to R is a differentiable function such that f0 is 0, f1 is 2 and f2 is 1. We have to prove that there exists at least one C in the interval 0 to 2 such that f dash C is equal to minus 1 by 2. Now this what we'll do is, since we are given that this function fx is differentiable in closed interval 0 to 2, we'll apply Lagrange's mean value theorem for this function fx first in the interval 0 to 1. Now since this function is continuous and differentiable, then Lagrange's mean value theorem says there exists a point C1 in the interval 0 to 1 such that f dash C1 will be equal to f1 minus f0 upon 1 minus 0, and here the value of f1 is 2, so it will be this 2 minus 0 upon 1 minus 0, which is 2. And if we apply Lagrange's mean value theorem on this function in the interval 1 to 2, then there exists at least one C2 in the interval 1 to 2 such that f dash C2 will be equal to f2 minus f1 upon 2 minus 1, and here value of f2 it is 1, value of f1 is 2, and here it is 1, so this value is minus 1. So basically f dash C1 it is 2 and f dash C2 it is minus 1. Now this function fx, it is a differentiable function. Now f dash C2 is minus 1 and f dash C1 is 2, and we know that minus 1 by 2 it lies in this interval between minus 1 and 2. Then using this corollary we can say there exists at least one C in the interval C1 and C2 such that f dash C will be equal to minus 1 by 2, and this interval C1 C2 it's a subset of this interval 0 to 2. That means there exists at least one C in this interval where this derivative will be minus 1 by 2. And the ninth one is, if we have a function fx which is differentiable at x equal to a, then mod of fx will be differentiable at x equal to a if f is unequal to 0. Now here the question is, we are given this function fx which is 2x into under root of x cube minus 1 plus 5 under root of x into under root of 1 minus x to the power 4 plus 7x square into under root of x minus 1 plus 3x plus 2. And we need to find its continuity and differentiability at x equals 1. Now first we'll find domain of this function. Now since we have square root, this x cube minus 1, it should be greater than or equal to 0. That means x is greater than or equal to 1. Now for this we'll get x is greater than or equal to 0. Now for 1 minus x to the power 4, it should be greater than or equal to 0, or x to the power 4 minus 1 should be less than or equal to 0. We'll have minus 1 plus 1, and this is plus minus and plus, so we'll get x should lie between minus 1 and plus 1. Here x is greater than or equal to 1. Now if we take intersection of all these intervals, then this function is defined at only one point. So this function is defined only at x equals to 1, and the value of this function at 1 is, now this is 0, this is 0, this is 0,
and 5. So basically this function, it is defined only at this point 1, and at this point its value is 5. So it is an isolated point. Now at 1 there is no neighborhood, neither on the left hand side nor on the right hand side. Now we have an isolated point. And then literature says at this point the function will be continuous but not differentiable. So the function is continuous but not differentiable at x equals to 1, and that's your option A. In this video, we'll discuss a very interesting and unique problem in differentiability. Now it says that we are given a function f which is an injective function, that is it is 1 1 in the domain a to b and range c to d. If alpha is the point in open interval ab such that f has left hand derivative L and right hand derivative R at this point x equals alpha, where both L and R are non-zero and they are different and they are negative, then we need to find left hand derivative and right hand derivative of its inverse function at x equals fa respectively. So there is a lot of information given for this question. Now we are given this function which is 1 1 and which is defined from a to b, and then it says it is not differentiable at alpha. Now its left hand derivative at alpha is L, which is negative, and its right hand derivative at alpha is R, which is also negative. Now say we have this point alpha. Now left hand limit at alpha is L, which is negative. So that means this function is decreasing in the left neighborhood of alpha, and right hand derivative is R, which also is negative but different. So on the right neighborhood of alpha also this function will be decreasing but with different slope. Now we need to find left hand derivative and right hand derivative of f inverse at x equals f alpha. Now this function, it is defined in the domain a to b and its ranges from c to d. Now at alpha, if we draw this left hand derivative, its slope is L, and in the right neighborhood of alpha this slope is R. Now we know that for inverse function we just have to take reflection of this function about y equals x line. So if we draw this y equals x line and if we take reflection of this function about y equals x line, then this function will be drawn like this and this part will be drawn like that. So we have this point now. Now this is alpha and this is f alpha, because this point was alpha and f alpha, and for inverse function x and y they interchange. So this point is alpha and f alpha. Now if we look at this left hand side tangent at alpha. Now suppose this is delta x and here it is delta y. So we can write delta y upon delta x, it is equal to L. Now if we take the reflection of this tangent about y equals to x line, then it will be drawn like this. Now here delta x and delta y, they'll interchange. So in this case, whatever was delta y will now become delta y will become delta x. So in this case, slope of this tangent, it will be delta x upon delta y. And this delta x upon delta y is nothing but 1 by L. Here if we look at this graph, then for this function fx, it was left hand derivative, But for this inverse function f, it is on the right side of f alpha. So that means right hand derivative of f inverse x at x equals f alpha, it will be 1 by L. Now in the same way, if this is R and if we take its reflection, here it will be this 1 by R. So previously, which was right hand derivative for fx, now translates to reciprocal of left hand derivative of f inverse x. So left hand derivative of f inverse x at x equals f alpha will be 1 by R. So answer to this question will be 1 by R and 1 by L. So previously for fx, left hand derivative is L, but for f inverse, left hand derivative is 1 by R, and for fx, right hand derivative is R, whereas for inverse, its right hand derivative is 1 by L. So that is the difference between the two functions. Now all this is very difficult to visualize in a graph. So what we'll do is, we'll try and solve this question analytically. Now we are given this function. So again, we'll draw the function. So we are given this function f, which is 1, 1, and at alpha, it is not differentiable. This point is f alpha. Left hand derivative at alpha, it is L, and right hand derivative at alpha, it is R. Now for this function, we clearly know that it is a decreasing function, which means f alpha minus h, it is greater than f alpha and will be greater than f alpha plus h. Now left hand derivative at alpha, which is f dash alpha negative, it can be expressed as this limit h tends to 0, f alpha minus h minus f alpha upon minus h, it is L, and right hand derivative at alpha will be this limit h tends to 0, f alpha plus h minus f alpha upon h, and this is equal to R. So this is already given in the question. Now what we'll do is, we will let beta equals f alpha. So this point, this is beta. Now if we increase beta, that is if we write beta plus h, then if we increase beta, which is say beta plus h, it is increasing the value. That means we are moving towards the left hand side of alpha. So that means this is equal to f alpha minus h dash, and if we are decreasing the value of beta, then beta minus h dash, we are moving towards right of alpha. So then will be this f and alpha plus some small value h dash. Now we'll start writing derivatives of its inverse function. So left hand derivative of f inverse at beta, which is f alpha, will be this beta negative, and we'll write this as limit h tends to 0, f inverse beta minus h minus f inverse beta upon minus h. Now basically f inverse beta minus h is alpha plus h dash. So we can write this as alpha plus h dash minus f inverse beta is simply alpha minus alpha upon, and then this minus h, we can write this minus h as f alpha plus h dash minus beta. Now here alpha will cancel, and when h tends to 0, h dash also tends to 0. Now this is limit h dash tends to 0, h dash upon f alpha plus h dash minus beta, and beta is f alpha. Now we can also write this as limit h dash tends to 0, 1 upon f alpha plus h dash minus f alpha upon h dash. And basically this is nothing. This is right hand derivative of this function f in the neighborhood of alpha. So this is right derivative at alpha, and right derivative at alpha is 1 by r. So left hand derivative of this function at fa, it is 1 by r, and in the same way we can find its right hand derivative. Now we can write its right hand derivative as f inverse beta positive, and this is limit h tends to 0, will be this f inverse beta plus h minus f inverse beta upon h. Now f inverse beta plus h is alpha minus h dash. So it will be this limit. Now h dash tends to 0, and this is alpha minus h dash, and f inverse beta is alpha. And again we can write this h as f alpha minus h dash minus beta. F alpha minus h dash minus beta, and beta is f alpha. Now here alpha and alpha will cancel, so we can write this as this limit h dash tends to 0, and we'll rearrange this as f alpha minus h dash minus f alpha upon minus h dash, which is nothing but left hand derivative alpha, and which is 1 by l. So left hand derivative is 1 by r, and right hand derivative is 1 by l. So we have solved this question graphically as well as analytically. Now here the question, we are given this function fx, which is defined in this way. Now if you look at the coefficient, this is 1, 5, 10, 10, and here it is 3 and 1. So what we'll do is we'll add 2x and subtract 2x. Now this is binomial expansion of x plus 1 to the power 5. So we'll write this function fx as x plus 1 to the power 5 minus 2x. When x is less than 0, it is x square minus x plus 1. When x lies between 0 and 1, it will be 2 by 3 x cube minus 4x square plus 7x minus 8 by 3 when x lies between 1 and 3, and it is x minus 2 log x minus 2 minus x plus 10 by 3 when x is greater than or equal to 3. Now for this function, if we look at f dash x, it will be this 5 x plus 1 to the power 4 minus 2 when x is less than 0. Now this is 2x minus 1 when x lies between 0 and 1. It will be this 2x square minus 8x plus 7 when x lies between 1 and 3, and it will be log x minus 2 plus 1 minus 1. So it will cancel when x is greater than 3. Now if we put the value 0, f dash 0 negative, it will be 5 minus 2, which is 3, and f dash 0 positive, it will be minus 1. So not differentiable at 0. F dash 1 negative, it is 1, and f dash 1 positive, it will be 1. So it is differentiable at 1, and f dash 3 negative, it will be 9, 18, 18 plus 7, 25, 25 minus 1, 1, and f dash 3 positive, it will be log 1, 0. So not differentiable at 3. Now if we draw the graph of this f dash x when x is greater than 0, when x is 0, this value is minus 1. At 1 by 2, this value is 0, and at 1, this value is 1. So that is the graph 2x minus 1. Now between 1 and 3, it is this quadratic equation. Now if x is 1, this value is 1. Now it will have its minimum value at 4x minus 8 equals 0, that is at x equals to 2, and at 2 this value will be 8 plus 7 minus 16, which is minus 1. And then we have the graph of log x minus 2. Now clearly at 1 we have two tangents, so it is not differentiable at x equal to 1. F dash x, it has a local maximum at x equal to 1, so this option A is correct. Now C is f is on 2. Now in this interval, at minus infinite, it will be minus infinite, and at 0, this value will be 1. So it will take the value, it will take all the values between minus infinite and 0. So we do not know about its shape. What we do know is range of this function will always contain this set from minus infinite to 1. Here this function is restricted, this is also restricted. So what we'll do is we'll first find the range of this function in this interval, and then if need be, we'll solve these two. So if you look at this fourth interval, that is when the value of x is greater than or equal to 3, this phi is x minus 2 log x minus 2 minus x plus 10 by 3. We have already worked out its derivative. Its derivative is dy by dx is log x minus 2, and it is greater than or equal to 0. That means this function, it is an increasing function in this interval. So its minimum value will occur when the value of x is 3. So this y3, it will be 1, and log 1, it is 0, and then this is minus 3 plus 10 by 3. So its minimum value is 1 by 3, and now we'll find its maximum value, which will appear at infinite. So if we take this limit x tends to infinite, now this x minus 2 log x minus 2 minus x plus 10 by 3. Now what we'll do is we'll add 2 and subtract 2. So we'll take x minus 2 common, and it will be log x minus 2 minus 1 and then minus 2. Now we take x tends to infinite, this is infinite and this is infinite, so its maximum value is infinite. So for this function, its range is from 1 by 3 to infinite. Now in between these two, they contain all the values from minus infinite to plus infinite. So range of this function is R, and therefore this function is an onto function. Now D is f is increasing on minus infinite to 0. Now if we find this f dash, so it will be this 5 x plus 1 to the power 4, it is equal to 2 when x is less than 0, and since we'll get real roots for x less than 0, this function is not strictly increasing in minus infinite to 0. So f is not increasing on minus infinite to 0. The correct options are A, B and C. Now the question is, we are given this function fx, which is x, and here we'll take 1 minus x common, and then it'll be this log x when x belongs to 0 to infinite. And then we have 3 columns, and there are 4 statements in each column. We have to work out which of these statements are correct and which of them they are incorrect. Now if we find f dash x, it will be 1 and then 1 minus x into 1 by x and then minus log x. So it will be simply 1 by x minus log x. So that's your f dash x. Now if we find f double dash x, it will be minus 1 upon x square and then minus 1 upon x. Now since x is positive, f double dash x is negative. And if f double dash x is always less than 0, it means f dash x is a decreasing function. Now since f double dash x is less than 0, it will be this concave graph. We have to work out this graph using some values. Now we are given points 1, e and e square. Now if we find f1 will be 1, fe will be, this is e and 1 minus e, fe is 1, and fe square will be e square plus 2 into 1 minus e square, which is 2 minus e square, and that is less than 0. Now this function f, it is continuous and differentiable. Then from Rolle's theorem we can say there exists a point c in the interval 1 to e where f dash c is 0. So it'll have a maxima between 1 and e, and at e square this value it will be negative. So this graph, it should be drawn like that. Now we'll work out values at 0 and infinity. Now if we take this limit x tends to 0 positive fx, it will be this limit x tends to 0 positive, and this is x plus 1 minus x into log x. Now this is 0, this is 1 into log 0, and log 0 approaches minus infinite. So this graph, it starts from minus infinite, and limit x tends to infinite fx, it will be this limit x tends to infinite x plus 1 minus x into log x. Now we have to work this limit out, and for this what we'll do is we'll let x as 1 upon t. So it'll be this limit t tends to 0 positive, and here it will be this 1 upon t, and this is 1 minus 1 upon t and log 1 upon t. So we can simplify this as limit t tends to 0 positive, we'll take t common, and here will be this 1 plus, and it will be 1 minus t into log t. Now we'll find its limit. Now this is log 0 is minus infinite upon 0 is not an indeterminate form but minus infinite. So at infinite it will be this minus infinity. Now we'll draw this approximate graph. It'll start from minus infinite, it'll take its maximum somewhere between 1 and e, and then at infinity it'll be again minus infinity. So here we'll have this point 1, and then e, it'll be this e square, and we'll have a point of local maxima in between 1 and e. Now we'll start evaluating these statements. Now fx is 0 for sum 1 and e square. Now between 1 and e square there is this one root, that means the statement 1 is correct. F dash x is 0 for sum 1 and e, this is Rolle's theorem. F dash x is 0 for sum x belongs to 0 to 1. F dash x is not 0 because there is neither maxima nor minima between 0 and 1. So this statement 3 is incorrect, and f double dash x is equal to 0. Now f double dash x, it is always negative. So that means this statement 4 is also incorrect. Now limit x tends to infinite fx, it is not 0, it is minus infinite. This we have already worked out. Now limit x tends to infinite f dash x. Now if we look at this f dash x, and if we take this limit x tends to infinite, 1 upon infinite is 0, and then minus log infinite is infinite. So we'll approach minus infinity, and limit x tends to infinite f double dash x. Now 1 upon infinite is 0, this is also 0. That means this limit is also correct. Now f is increasing on 0 to 1, correct. Decreasing on e to e square, that's also correct. Now f dash x, it is a decreasing function. So that means this statement s is correct. Now we need to choose the correct combinations. Now which of the following options is the only correct combination? And the first one correct is 1 and 2. So this a is incorrect, c is incorrect. So here we have 1 and 2. And the second and third, they are both correct. And then from r and s is correct. So this is your option D. Now the next one is which is the only correct combination? Now third and fourth incorrect, first and 2 correct. Now here first is incorrect, so the correct combination is this D. And the next one is which of the following is the only incorrect combination? Now this is 1 2 and this is 2 3. So this 3, it is not defined. Here 1 is not defined, and here r is not defined. So this again is this option D. So for all three of them, the correct option is D.
Now question number 25 is, we are given this function such that f3 equals 3 times f dash 3 and it is a positive number. Then this limit x tends to infinite, f3 plus 3 upon x upon f3 to the power x is. Now if we look at this form is 1 to the power infinite form. And for 1 to the power infinite form, we have this shortcut that we can express it as e to the power, this limit x tends to infinite, gx into fx minus 1. So it will be f 3 plus 3 upon x upon f3 minus 1. So we can write this limit as e to the power limit x tends to infinite, f 3 plus 3 upon x minus f3 upon f3 1 by x. Now what we will also do is we'll multiply by 3 and divide by 3. Now this is nothing but this is f a plus h minus fa upon h, and that is nothing but derivative of this function at a. So we can write this as e, and it'll be 3 into f dash 3 by f3. Now in the question it says 3 into f dash 3 by f3 is 1. So this value, it is equal to e to the power 1, which is e. So this limit, it exists and is equal to e, and that's your option B.
Now here the question is, we're given that f0 is 0 and f dash 0 is 1. For some positive integer case, show that this limit x tends to 0, 1 by x, fx by 2, f x by k, it is equal to 1 plus 1 by 2 plus 1 by 3 up to 1 by k. Now we can write this as limit x tends to 0, and then this summation f x by r, where r varies from 1 to k upon x. Now first we'll check its form. Now we put x as 0, it will be f0, and f0 is 0, and x, it is 0. So this is 0 upon 0 form, and if it is 0 upon 0 form, we can use L'Hopital's rule. So we can write this as limit x tends to 0, and then this summation r varies from 1 to k, and it will be this f dash x by r into 1 by r upon 1. Now this is summation r varies from 1 to k. This is f dash 0 upon r. Now f dash 0 is 1. So it will be this summation r varies from 1 to k, 1 by r, which is nothing but 1 plus 1 by 2 up to 1 by k. And this is what we need to prove in this question. Now here the question is, let f and g be real valued functions defined on the interval -1 to 1 such that g double dash x is continuous, g0 is unequal to 0, g dash 0 is 0, g double dash 0 is unequal to 0, and fx is gx into sin x. Now we have to find validity of these two statements. Now this is f dash 0 equals g0. Now we are given fx equals gx into sin x. Now we let f dash x as gx into cos x plus g dash x into sin x. Now if we put x as 0, we'll get f dash 0 as g0, cos 0 is 1, and then g dash 0 and sin 0 is 0. Now in the question it says g0 is unequal to 0. So from here we can say this f dash 0, it is equal to g0. That means the statement 2 is correct. Now second one is, we'll check this limit. Now this limit is limit x tends to 0. Now we'll write this as gx, and we'll change it in sin and cos. So it will be gx cos x minus g0 upon sin x. Now this is 0 upon 0 form. We'll use L'Hopital's rule. We can write limit x tends to 0 gx sin x plus g dash x cos x upon cos x. Now we put x as 0, it will be g0 into 0 plus g dash 0, cos 0 is 1, and here this value is 1. And the question it says g dash 0 is 0, so value of this limit is 0. Now if we find f double dash x, then f double dash x will be gx minus sin x plus g dash x into cos x plus g double dash x sin x plus g dash x into cos x. Now if we put x as 0, we get f double dash 0 as g0 and sin 0. Sin 0 is 0. Now g dash 0 is 0. Now sin 0 is 0. And here g dash 0 is 0. So f double dash is 0. So it will be equal to f double dash 0. That means this statement 1 is also correct. Now value of this limit is equal to 0, which is also the value of f double dash 0. But these two results, they are not correlated. So basically both the statements are correct, but statement 2 is not a correct explanation of statement 1. So the answer is this option B.
Now in question number 9, we are given a continuous function f, and then we have defined two sets. Set T, which is set of slopes of all possible tangents to the graph of f, and then there is this set S, which is set of slopes of all possible secants, that is line joining 2 points on the graph of f. Now the first one is, if f is differentiable, then S is a subset of T. So if we take any secant, which is say fx1 minus fx2 upon x1 minus x2, then from Lagrange's mean value theorem, we can say that there exists at least one point C in the interval x1 and x2 such that slope of tangent at C is equal to secant slope. So for any possible combination of x1 and x2, we always have point where tangent is equal to secant. So that means S is a subset of T. That means statement 1 is correct. So it is true. Now second is, if f is differentiable, then T is a subset of S. Now S must be a subset of T, but then T may not be a subset of S. So this second statement, it may not be necessarily true. So this second statement is false. We can take up an example also. Say for example, suppose function fx is sin x. If we find f dash 0 is cos 0 is 1. Now 1 belongs to T. But then if we look at the secant set, then sin x minus sin y upon x minus y, it is always less than 1. So 1 belongs to T, but it doesn't belong to the secant set. So that means the second statement is false. Now this third one is, if T is equal to S is equal to R, then f must be differentiable everywhere. It may not again be necessarily true. We can have a function where tangent set and secant set, they take all real values, but still that function may be a discontinuous function, as in the example of 10x. So again, statement 3 is not correct. So this is false. Now what about fourth one? Suppose it says 0 belongs to S and 1 belongs to S. Then every number between 0 and 1 must also be in S. So at some point, slope is 0, and then at some other point, slope is 1. Now since the function is a continuous function, from mean value property we can say that slope of all possible secants will take all the values between 0 and 1. So that means statement 4 has to be true. So answer to this question is true, false, false and true.
Now the next question is, a real valued function f is defined on the interval -1 to 2. A point x0 is said to be a fixed point if f x0 equals x0. Now suppose that f is a differentiable function such that f0 is greater than 0 and f1 is equal to 1. Show that if f dash 1 is greater than 1, then f has a fixed point in the interval 0 to 1. Now what we'll do is we'll consider a function hx which is given by fx minus x. Now since f is differentiable and x is differentiable, this function hx, it is also a differentiable function. Now value of h0 will be f0 minus 0 and f0 is greater than 0. So this h0, it will be greater than 0. And what about h1? h1 will be f1 minus 1, and since f1 is equal to 1, that means value of h1 is 0. Now we differentiate this function, we can write h dash x as f dash x minus 1, then h dash 1 will be f dash 1 minus 1, which is greater than 0, that is at 1. This function hx, it is an increasing function. So if we consider this function, then this is hx and this is x, this is 0. Now h0 is equal to f0 and h1 is 0, and here it is an increasing function. So this graph, it starts from some positive number and then at 1 it will be an increasing function. So that means there will be at least one point between 0 and 1 where hx is 0, and suppose this point be x0. So there will be at least one x0 in the interval 0 to 1 such that hx0 is 0. Now what is hx0? It is fx0 minus x0 equals 0. That is the value of fx0 must be equal to x0. That means this f, it has a fixed point in the interval 0 to 1. Now question number 4 is, let f be a twice differentiable function in the open interval minus 1 to 1 such that f0 is 1. Suppose f also satisfies fx greater than or equal to 0, f dash x less than or equal to 0, and f double dash x is less than or equal to fx for all x greater than 0, then show that f dash 0 is greater than or equal to minus root 2. Now it is given that this function f, it is a twice differentiable function, so we can use Taylor's polynomial theorem. We can write fh will be equal to f0 plus f dash 0h plus f double dash theta h square upon 2, where theta lies between 0 to h. Now since f double dash x, it is less than or equal to fx, we can write f double dash theta will be less than or equal to f theta. Now since f dash x, it is less than or equal to 0, it simply means fx is a decreasing function, and if fx is decreasing, then f0 will be greater than f theta. So f theta will be less than or equal to f0. fh, it will be less than or equal to f0 plus f dash 0h plus f0 h square by 2. Now f0 is 1, so we can write fh, it is less than or equal to 1 plus f dash 0h plus h square upon 2. Now we know that f double dash x is less than or equal to fx, so we can say this fh will be greater than or equal to f double dash h. Now we'll integrate both sides from 0 to x. So we can write f dash x minus f dash 0 will be less than or equal to x plus f dash 0 x square upon 2 plus x cube upon 6. Now we'll integrate this once again from 0 to x. Here will be fx minus f0 minus f dash 0x, and it will be less than or equal to x square by 2 plus f dash 0 x cube by 6 plus x to the power 4 by 24. Now we'll take f dash 0 together. So we can write f dash 0 x plus x cube upon 6, it is greater than or equal to minus x square upon 2 minus x to the power 4 upon 24 plus fx minus f0. Now f0 is 1 and fx is always greater than or equal to 0. So from here we can say f dash 0 into x plus x cube upon 6 will be greater than or equal to minus x square upon 2 minus x to the power 4 upon 24 minus 1. And from this we can write f dash 0 will be greater than or equal to minus x square by 2 minus x to the power 4 upon 24 minus 1 upon x plus x cube by 6. I'll be true for any x which lies in the interval 0 to 1. Now this function on the right, it is an increasing function. So this f dash 0 will always be greater than or equal to the value when the value of x is 1. So if you put x as 1, we'll get this as minus 1 by 2 minus 1 by 24 minus 1 upon 1 plus 1 by 6. So it will be minus 37 upon 28, which is nearly minus 1.32. So from here we can say this f dash 0 will be greater than or equal to minus root 2, and that is the answer to this question.
Now question number 3 is, let this function f be defined from R to R such that mod of f x plus y minus f x minus y is always less than or equal to y square. Now we need to show that fx is x by 2 plus c, where c is a constant. Now what we'll do is we'll try and rearrange this functional equation. So we'll let this x plus y as some t plus h and x minus y as t. Now we subtract the second from first, we'll get y as h by 2. So we can write this as mod of f t plus h minus ft minus h by 2, and will be less than or equal to h square by 4. Now mod x is less than a, then x lies between minus a and plus a. So we can write minus h square by 4. It is less than or equal to f t plus h minus ft minus h by 2, and will be less than or equal to h square by 4. Now we'll add h by 2. So we can write h by 2 minus h square by 4 will be less than f t plus h minus ft, and will be h by 2 minus h square by 4. Now we'll divide everything with h, and we'll take this limit h tends to 0. Now this value, it is 1 by 2. Now this is nothing but this is f dash t, and this limit, it is also 1 by 2. So from here we can say this f dash t, it is 1 by 2. Now we integrate this function, we write ft as 1 by 2 plus c, or we can write this function fx will be simply x by 2 plus c, where c is a constant. And this is how we solve such question. Now question number 4 is, let f and g be two non-decreasing twice differentiable functions. So that means f dash is greater than equal to 0 and g dash is also greater than equal to 0, such that f double dash x is equal to gx and g double dash x is equal to fx. Then suppose that fx gx is linear on x on AB, then show that we must have fx equals gx equals 0 for all x belongs to AB. Now it is given that fx into gx, it is a linear function, say px plus q. Now we'll differentiate, we'll get f dash g plus g dash f and L be equal to p, and we'll differentiate again, we'll get f double dash g plus f dash g dash plus g dash f dash plus g double dash f and L be equal to 0. Now f double dash x, it is gx and g double dash x is fx. So we can write gx square plus 2 f dash x into g dash x plus fx whole square and L be equal to 0. Now this is 0 or greater than 0. Fx square is also 0 or greater than 0, and f dash x is greater than equal to 0 and g dash x is greater than equal to 0. So this is also greater than or equal to 0. Now sum of positive real numbers, it cannot be 0. It can only be 0 if each of them are individually 0. So it simply means that this function gx is 0 and fx is 0 when x lies between a and b. And this is how we solve such questions. Now in question number 22, it says f be any twice differentiable function such that its second derivative is continuous and f dash x, it is unequal to 0 for all x unequal to 0. Now if limit x tends to 0, fx upon x square equals pi, then which of the following is correct? And this we have also proved in one of the previous papers. I think that was 2010 or 2011 paper, where we have proved that value of f0 will be 0 and f dash 0 will also be 0. Now if it is 0 upon 0 form, then we can write f double dash 0 upon 2 will be equal to pi, that is f double dash 0 will be simply 2 pi. Now since f dash 0 is 0, that means x equal to 0 is a critical point, and f dash 0, it is greater than 0, that means this x equal to 0 is a point of local minima. So at 0, this function will be concave up and it will also have a point of local minima at x equal to 0. And since fx is unequal to 0, that means at no other point it will have a critical point. So this is the only critical point possible in this case. So at 0, we have a double root, that is concave up. Now after x is greater than 0, this function will increase because there is no other critical point. And on the left hand side also, this function will be a decreasing function. This function cannot increase when x is less than 0 because it will contradict our given condition where f dash x is 0 and f double dash x is positive. So this f0, it is the least possible value of this function. That means fx is greater than f0 for all x unequal to 0, and that's your option A. Now question number 1a is, for any polynomial pt, the limit t tends to infinite pt upon e to the power t is independent of polynomial p. Justify the statement and find the value of this limit. So we have this limit which is limit t tends to infinite p as a function of t upon e to the power t. Now if we put t as infinite, this numerator will be plus or minus infinite, and then e to the power infinite will be infinite. So when it is infinity upon infinity form, we can use L'Hopital's rule. And if we use L'Hopital's rule, we can write this as limit t tends to infinite p dash t upon e to the power t. Then again L be plus minus infinity upon infinity. So we can differentiate it again. We can keep using L'Hopital's rule till we differentiate this function n times, which is degree of this polynomial. And if we differentiate this polynomial up to its degree, then it will be some constant upon infinite, and any constant upon infinite is simply 0. So this statement is true and the value of this limit is simply 0. So that's your part A. Now part B is show that q dash 0 exists and find its value. And why is it enough to calculate the relevant limit from only one side? Now we'll find q dash 0 positive. Now q dash 0 positive will be limit h tends to 0, q 0 plus h minus q0 upon h. Now this is limit h tends to 0. Now q h positive when x is greater than 0 is simply e to the power minus 1 by h. q0 is 0 and here it will be this h. So we can write this as limit h tends to 0, 1 by h and then e to the power 1 by h. Now what we will do is we let 1 by h as t, then we can write this as limit t tends to infinite t upon e to the power t, which is of the form pt upon e to the power t, and we know that this limit is equal to 0. So q dash 0 positive is 0. Now we need not calculate q dash 0 negative as this given function is an even function. So suppose we have to find the value of q minus 2 will be e to the power minus 1 by 2, and which is same as value at 2. So this given function is an even function. So we just have to calculate limit from only one side. So this q dash 0 exists and its value is simply 0. Now part C is for any positive integer n, show that qn0 exists and find its value. Here qx is the function in part B and qn0 denote the nth derivative at x equals 0. Now what we'll do is for this part C, we have to find nth derivative of this function at 0. Now we know that qx, it is an even function. Now if qx is even, q when x is odd, q2x is even and continues. So we can say this q and x will be even when n is even and will be an odd function when n is an odd function. So we can simply write qn minus x will be minus 1 to the power n q nx. Now if we look at this function, which is qx when x is greater than 0, it is e to the power minus 1 by x. Now q1x will be e to the power minus 1 by x into 1 upon x square. Now we find q2x will be e to the power minus 1 by x minus 2 upon x cube plus 1 upon x square e to the power minus 1 by x and then 1 by x square, which is e to the power minus 1 by x minus 2 upon x cube plus 1 upon x to the power 4. Now we keep differentiating it. We can write qnx will be of the form e to the power minus 1 by x and then some polynomial expression of 1 by x. Now if we have to find qn0 positive, it will be this limit h tends to 0 e to the power minus 1 by h p 1 by h. If we let 1 upon h as t, we can write this as limit t tends to infinite pt upon e to the power t, and this we have already established in part A that this is equal to 0. So from here we can say this qn0 positive will be equal to qn0 negative and will be equal to 0. That is this q and 0 will exist and it is equal to 0.